Our next talk is by Jorge Fariña-Asategui and from Lund University. So take it away.
Okay, good afternoon. First, thank you for this invitation. I'm very happy to talk here today. So I will talk about a generalization of iterated permutational wreath products and some applications to the Hausdorff dimension of some cell-similar profinite groups. So first, I will describe groups acting on regular rooted trees, and I will show how we can define iterated permutational wreath products in this context. Then I will discuss several generalizations of these iterated permutational wreath products. And finally, I will show an application to the Hausdorff dimension of cell-similar profinite groups. So first, I start with groups acting on regular rooted trees. So first, we fix some m, at least 2, a natural number, and we'll define the magic tree, Tm, as the rooted tree such that each vertex has m immediate descendants. So we have here the root has m descendants, and its descendants has itself m descendants, and so on up to infinity. So an alternative description of the magic tree could be to fix a set X of m elements, and then just identify the magic tree with the set of words on X. So in this context, the root would just be the empty word, and its vertex would be identified with the worm formed by the labels in the path from the root to it. So for example, the vertex here would be the vertex 1, 2, because it's the path that goes from the root to this vertex. And the set of words that are of length n in this context are the nth level of the tree. So we can see here the first level of the tree, the second level of the tree, and so on. So our object of study will be the group of automorphisms of the magic tree. So an automorphism of the magic tree will just be a graph automorphism. It will act by permuting the vertices at the same level. And we'll denote this group of automorphisms by out Tm. And a very important family of subgroups of the full automorphism group is the one of level stabilizers, which are those normal subgroups consisting of automorphisms fixing a given level. So to give you an example, we have here the first level stabilizer, and its elements will fix both the root and the vertices at the first level of the tree, and they may permute the ones that are at the second level, third level, and so on. So a very convenient way to work with these automorphisms of the magic tree is given by an isomorphism called psi. And in order to define this isomorphism, we need some notation. So we will fix an automorphism f of the magic tree and some vertex v. Then we can define the section of f at v as the action of f on the subtree rooted at v. So we look at how f acts on the vertices that are below v. And then we have the label of f at v, which is by looking just at how f acts on the immediate descendants of v. So then the label is just going to be a permutation of the symmetric group because it tells you how it permutes the descendants of v. And the section can be identified with an automorphism of the original tree. We'll see this identification in the next slide in an example. I want to mention also that you could define something intermediate like an nth level where you look at the action of f on the vertices that are at distance n from v, and this will appear later on, so just for you to keep in mind. And then with this notation, we can define the isomorphism psi that I mentioned before by mapping every automorphism to a tuple consisting of the sections of this automorphism at the first level of the tree times the label at the root. So in order to see this better, I think it's better to use an example. So here we have an automorphism f. We consider the sections f1, f2, fm, and the label. And we can see how the action of f can be described using this construction. So the label will tell you that f acts by permuting at the first level of the tree the first vertex and the second one. It will interchange those and leave the other ones invariant. And then f1, f2, fm control how f acts on these rooted subtrees at the first level. And the identification I was mentioning before comes from the emadic tree being a fractal object. So if we consider the subtree rooted, for example, at the first level of the tree, this is identical to the full emadic tree. So if we just move everything rigidly from the first level, from the first vertex here to the root, we say that the section F1 can be identified with an automorphism of the original tree. So whenever we talk about these sections being in some subgroup, we will usually use this identification. So now we are in position to define iterated permutational wreath products in this context. So for this, we fix some subgroup H of the symmetric group on M symbols, and we can define the iterated permutational wreath product WH as a subgroup of the group of automorphisms of the emadic tree by just considering the automorphisms whose labels lie all in H. So basically, these are automorphisms whose local actions are given by elements in H. So some important examples include, of course, the full automorphism group. So this just corresponds to the symmetric group. So we are not making any extra restriction here. And another important case is the group of p-adic automorphisms, which is given by the subgroup generated by the p cycle sigma for some prime p. And a bit more generally, we have the group of quadic automorphisms, where Q is not a prime, but a prime power. So I want to make a small remark, because usually iterated permutational wreath products may be considered from a finite group H acting on some finite set X, and this action could be non-faithful. Then we are not in this case where H is a subgroup of the symmetric group. But still, in this case, one can extend this action to the free monoid generated by X. And we saw in the first slide that this is the emadic tree. And in this context, one can define also WH similarly, like Penland and Sunitz did, a bit more generally for self-similar groups, not only for iterated permutational wreath products. And I want to mention that what I'm going to talk about works in this more general context too, but for simplicity, I think it makes sense to assume that this action is faithful, so that we can consider H to be a subgroup of the symmetric group of the set X. So now I will fix some subgroup of the full automorphism group G, and we have some important subgroups to consider. So the level stabilizers are defined similarly. So we consider the automorphisms in G that also fix the nth level of the tree. And a bit more subtle definition is the one of wreath stabilizers. Here, we first define the wreath vertex stabilizers, which are the subgroups consisting of automorphisms that only act on the subtree rooted at B. So you have a vertex B, and you want automorphisms that outside of B, they fix everything. So their action only permutes vertices that are below B. So it's easy to see that if you consider two different vertices, the corresponding wreath vertex stabilizers commute with each other. And if they are at the same level, they will be conjugate if the action is transitive. So then we can consider their direct product. And these are the ones that we will call wreath level stabilizers, which will be normal subgroups of G. And I will define some classes of groups that I'm interested in and that will appear later on in this talk. So we'll say that the group is level transitive when it acts transitively on every level of the tree. We'll say it is self-similar if the sections of G are all, again, elements in G after this identification that I mentioned before. The dual notion of branching will be when a group K contains copies of itself after applying this isomorphism psi. So you can think of it like a group containing copies of itself, so being some kind of fractal object. And then we have a stronger notion of self-similarity, which is super strongly fractal. So for this, we ask the group to be self-similar, and not only that the sections are, again, elements of G, but we want to see every element of G as a section of elements of the level stabilizers for every level. So we want that when we keep going down in the tree, we still see all the elements of G. And then the notion of branch is going to be a group that is level transitive and whose wreath stabilizers are finite-index. And weakly regular branch and regular branch will be self-similar groups that contain a non-trivial or finite index branching subgroup, respectively. So now we are interested in generalizing this concept of iterated permutational wreath products. So if we look at the definition, it's just that the local actions are given by some special subgroup of the symmetric group. But I mentioned before that there was this more general concept of labels that look at the action not only on the immediate descendants, but on the descendants that are at distance n from this vertex. So we could define something similar. And this is what the groups of finite type are. So we consider P as a group of the nth wreath product of the symmetry group on M symbols, and this will be called an M pattern. So a group of finite type, GP, for some M pattern P, will consist of the automorphisms of the magic tree whose nth labels are elements in P. So at this time, we just look at the action of the automorphisms at the descendants that are at distance n from a given vertex. And this was a concept introduced by Grigorchuk in 2005. And here he proved that if you have a level transitive profinite group, which is self-similar and of finite type, then it is also regular branch. And soon it proved the converse in 2007. So in the end, these groups of finite type are just regular branch groups. And some remark that we get from this definition is that there are only countably many groups of finite type, because they are in correspondence with n patterns, and for every n there is going to be finally many patterns, and there are countably many n's. So in the end, we only obtain countably many groups of this kind. And for our purposes, we need uncountably many different groups with different properties. So this is not going to be a useful generalization for us. So we'll try to find another generalization that gives a bigger family of groups. So for this, we'll use maybe a more classical construction of iterated wreath products. So we'll fix the notation h to the k will just be k copies of h. And then we can describe WH by considering first h, and then considering the semi-direct product with m copies of h, then semi-direct product with m to the square copies of h, and so on, and considering the inverse limit. Then this is another way to construct WH. And it has this property that the consecutive level stabilizer, the quotients of the consecutive level stabilizers are just copies of h. And we want to generalize this construction. So the first thing that we do is we see why this construction works, and we try to generalize it. So if we denote by Sn to the m to the n copies of h, and an to the first iterated, to the first n plus 1 iterated semi-direct products of these Sns, we see that these subgroups Sn are just the subgroups of m to the n copies of the symmetric group. And more importantly, the subgroup Sn is an minus 1 invariant. And this is what allows us to consider the semi-direct product of Sn with an minus 1. So an minus 1 just acts by permuting the components of Sn, because we are in a direct product. And this is the important thing. It's not important that Sn is just some copies of h. The important thing is that it is an minus 1 invariant. And whenever it is an minus 1 invariant, we can carry out some construction like this one. And this was our motivation to construct the groups GS. So I will show how we can construct such a group. So first we'll fix some S0 to be some subgroup H of the symmetric group. And similarly, A0 will be the same H. And then inductively, we choose Sn inside the m to the n copies of h in such a way that it is an minus 1 invariant, so that we can define an to be the semi-direct product of Sn with an minus 1. And as we do in the iterated wreath product case, we take the inverse limit, so we define the group GS to be this infinite product of these Sns, and this will result in a profinite group, which is completely determined by this sequence of groups S. And to give you some different example that is not an iterated wreath product, we can consider the group Sn, which is the diagonal of sigmas. So we put sigma everywhere on the subgroup generated by this. And for those of you who know, this is going to be just the closure of the subgroup generated by the adding machine, which is just a way to embed the integers as a group acting on the M-adic tree. So these are groups that actually appear naturally in this in the study of this kind of groups. And the nice thing about these groups is that we can study their properties just by looking at the sequence S. So for example, if you want to construct a cell-similar group GS, you only need to choose these subgroups inductively such that each one is contained in m copies of the previous one. If you want it to be branching, then you want each one to contain n copies of the previous one. And similarly, for super strong fractality, you want that it projects to the previous one. For level transitive, you want that it acts transitively on the set 1m for every n. And for branch, you just want to choose this Sn such that they are bigger and bigger natural direct products. So we can see that we can characterize these properties just in terms of the sequence S. So this will allow us to obtain profinite groups with the properties that we are interested in just by specifying a sequence that satisfies easier properties. And this is something interesting. So to show you an application of this construction, I will discuss the Hausdorff dimension of cell-similar profinite groups. So first of all, if we have a countably based profinite group G given by some filtration n, this filtration n will induce some natural metric in G. And using this metric, we can define some Hausdorff measure and therefore some Hausdorff dimension for the subgroups of G. So this was started by Abercrombie in 1994. And Barnett and Saleft proved in 1997 that for a closed subgroup H of G, the Hausdorff dimension of H in G is just given by the lower box dimension. So it's actually given by the lower limit of this fraction of the logarithmic indices of the corresponding group with respect to this filtration. So in our case of interest, we are interested in the automorphism group of the M-adic tree, or more generally, any iterated wreath product. And these are both profinite with respect to the filtration given by the level stabilizers. And this is probably the most natural filtration we can consider in this kind of groups. And therefore, the Hausdorff dimension in this case is given by the lower limit of the logarithmic indices of the level stabilizers. So in order to understand the Hausdorff dimension, it's enough that we understand the logarithmic indices of the level stabilizers of G, because the ones of the iterated wreath products are already understood. So the first question that arises here is whether we can get a better formula in the case that G is self-similar, because this formula is completely general. It was for any profinite group, but we suspected that for self-similar groups, the formula is actually, for example, given by a proper limit, and that we could do it in an easier way. So in order to show this, we need to define some special subgroups, which at first look a bit ad hoc, but they are not. So we consider the subgroup Sn to be the product of the image via psi of the first level stabilizer and m copies of the n minus first level stabilizer of G. So why do we define these kind of subgroups? If we want to understand the index of the nth level stabilizer in G, it's enough that we understand the index of the first level stabilizer of G in G, which is usually easy to compute. And then we understand this index here. But psi is an isomorphism. So this index here is the same as the index here after applying psi. And it's very easy to see that the image of the nth level stabilizer via psi is just the intersection of this subgroup here and m copies of the m minus first level stabilizer of G. So then we can apply the second isomorphism theorem to say that this index here is the same as this one here. But now we look at the big red index here, and this is completely given by the previous level stabilizer. So inductively, we can really compute these indices if we only know the indices of these subgroups Sn that we just defined here. So it's equivalent to know the logarithmic indices that we are interested in, and the logarithmic indices of these subgroups Sn. So we'll give a name to these logarithmic indices. We'll call them little rn. And then we can consider also the forward gradient of this sequence, which is just rn plus 1 minus rn. Or in terms of these subgroups, it's just the indices of consecutive subgroups. And now we have a sequence. We don't really know what to do with this sequence. So a very natural approach whenever you have such a sequence is to consider a generating function. So we consider the ordinary generating function of this sequence little sn, that we call a capital SG of x. And the first thing that we did was computing the convergence of this series. So in the case that the G is self-similar, we define this series, and we see that it converges at 1 over m, where m is the degree of the regular rooted tree it is acting on. And we only care about this point of the convergence. And the reason for this is the following theorem, because actually the value of this series at this point gives the Hausdorff dimension of G in WH. So if we consider a subgroup of WHG, which is closed and self-similar, such that the quotient with the first level stabilizer is H, as expected, then the Hausdorff dimension is just 1 minus this value of the generating function at 1 over m, divided by the logarithmic index of the first level stabilizer. So basically, this gives us a series expansion of the Hausdorff dimension. And this is going to be a very powerful tool to study this Hausdorff dimension, because if we are able to somehow have some control on the terms appearing in this series expansion, we'll be able to construct groups that have a prescribed Hausdorff dimension. And this is what we are trying to do. So to state the problem that we're interested in, we need a last definition, which is that of a restricted Hausdorff spectrum. So we fix a subclass of groups P, and we consider the set of the Hausdorff dimension of the closed subgroups of G that satisfy this property P. And we are going to study this kind of sets. So Grigorchuk asked in 2005 about the possible values of the Hausdorff dimension of closed self-similar groups, and whether these values had to be rational or not. So the first thing we did is we saw that we could reduce this problem of Grigorchuk from all closed self-similar groups to just the GS groups that are self-similar that we constructed before. So to show this, we fixed P to be one of these subclasses of groups, so either self-similar, branching, super strongly fractal, level transitive, weakly branch, weakly regular branch. And then we prove the following. If we consider the family of the GS groups that satisfy this property P, it is going to be universal with respect to the Hausdorff dimension, in the sense that if there exists a closed subgroup G of WH satisfying P, and with Hausdorff dimension alpha in WH, then there must exist a subgroup GS satisfying P, and also with the same Hausdorff dimension alpha in WH. So if we want to study this restricted spectra of iterated red products, then we only need to work with the groups GS. So we got this striking result for the group of quadic automorphisms. So we studied the following restricted Hausdorff spectra. So when we restrict to the subclass of self-similar, level transitive, and super strongly fractal groups, we obtain the full interval 0, 1. So any value in the interval 0, 1 can be realized as the Hausdorff dimension of a self-similar, level transitive, and super strongly fractal group inside the group of quadic automorphisms. So this already answers this problem of Grigorchuk. But we went a step ahead and also proved the following ones. So we proved that for self-similar and branch groups, we also obtain the interval 0, 1. But for weakly regular branch groups, we get every positive number, but not 0. So this is the only number that cannot be realized as the Hausdorff dimension of a weakly regular branch group inside the group of quadic automorphisms. And for regular branch groups, we get this subset of the rational numbers with denominators a prime power of P. And I want to mention that for weakly regular branch groups and regular branch groups, the same holds if we add the super strong refractality condition. However, for cell-similar and branch groups, this is no longer true, because we proved that for a closed cell-similar group, it is equivalent that it is regular branch and that it is virtually fractal and branch, where virtually fractal is like the weakest version of fractality that we have. So whenever you add any fractality condition to a cell-similar branch group, you end up with a regular branch group. So if you start here cell-similar branch group with some Hausdorff dimension, but you add some fractality condition, you will end up here, so you cannot get all these values with some fractality condition. And to conclude, I just want to give you a sketch of the proof of this theorem. So the idea is to consider an allowed dimension alpha, and then consider the Q-base expansion of 1 minus alpha, that we write as the series of alpha n over Qn. And then we use the theory of finite p groups to construct a sequence S such that the sequence small sn of GS will be given precisely by these alpha n's appearing in the Q-base expansion. And then, since the groups we are constructing are self-similar, we can use our new formula for the Hausdorff dimension to conclude that the Hausdorff dimension of the group GS in WQ is 1 minus this series of alpha n over Qn. But this was the Q-base expansion of 1 minus alpha, so this is just alpha. So we see that any allowed dimension is actually realizable as the Hausdorff dimension of a cell-similar group satisfying these special properties appearing in the theorem. And then to conclude, we have to prove the restrictions on the allowed dimensions. So for regular branch groups, we have that they have to be rational numbers with these prime power denominators. So this was proved by Bartoldi in 2006. And for weakly regular branch groups, we only have that they have to be positive. And this we proved this one also. And here there are the references to the results I mentioned in these slides, in case you want to have a look at them. And that's all. So thank you.
Okay, let's thank the speaker. Are there any questions for the speaker? Okay, so maybe this is a dumb question, but what Hausdorff dimensions are possible for, let's say, a self-similar group or?
So for a cell-similar group that is inside WQ, you can get any possible Hausdorff dimension, because you can even ask for more. You can ask for cell-similar and level transitive and super strongly fractal, for example. Or you could ask for cell-similar and branch at the same time. And then you can construct, I mean, the proof of this theorem is constructive. So we actually provide subgroups with these Hausdorff dimensions. And the idea is to construct a group of this kind, GS, that I described before. So we describe the sequence S, and then using this sequence S, we construct GS. By construction and using this formula, you know that the Hausdorff dimension is the one that you wanted.
Mm-hmm.
So any Hausdorff dimension can appear for self-similar groups.
Okay, thank you. Are there any other speakers? Any other questions for the speaker? Okay, if there are no other questions, let's thank Jorge again.